Okay, let's start now. Hello, everyone. Today, I'm going to talk about the security of Apple file system on iOS. And the title of my talk is The Last Line of Defense, Understanding and Attacking Apple file system on iOS. My name is Xiaolong Bai. I'm from Alibaba Orion Security Lab. Before joining Alibaba, I have published several papers on the Big Four. My Twitter account name is BXL1989. The co-author of this talk is Min Spark Zheng. He is a security expert from Alibaba, and his Twitter account name is Spark Zheng. Welcome to follow us on Twitter. In this talk, I will first introduce some background information of Apple file system and show some previous attacks. After that, I will explain how Apple file system has mitigated these attacks. Then I will show a new method to bypass these mitigations, and also discuss some other bypass methods. First of all, let's have a look at the basics of Apple file system. Apple file system is a new file system proposed by Apple on macOS 10.13 and iOS 10.3. It is designed to be high performance and high security. It's short. APFS is short for Apple file system. There are several important data structures in iOS file system and APFS in order to manage these file system and files. The most important one is mount, as we can see here. A mount structure represents a mounted partition in the system. And in this structure, the field mount flag represents how the partition is mounted. And the field mount data points to some private data structure that are organized by specific file systems. And another important structure is vnode. A vnode structure represents a file or directory in a partition. In this structure, the vmount field points to the vnode's belonging partition's mount structure, and the vdata points to private data organized by specific file systems. And this is a simple graph showing the relationship between mount and vnode, just as we have described. There is a critical partition in iOS and macOS, which is called root partition. This partition is mounted on the root directory. In this partition, there are several important directories holding important code and data for the system to run. For example, applications folder holds unsandboxed and system applications. Bin holder holds system binaries, and so on. In most of time, this is the main target for an attacker to control in order to modify system settings or install malicious apps. So on September 17th, 2018, Apple have published a manual called Apple File System Reference, which describes data structures used in APFS. This is a perfect reference for research. You can download it from the link. But when this talk was prepared and submitted, the reference manual has not been published yet. All knowledge in this talk is required by from reverse engineering. Next, let's have a look at previous attacks on APFS. As I have said, in most times, the root partition is always attacker's main target because it holds many important code and data. But by default, root partition is always read-only. In order to modify files or directories in this partition, attackers always have to remount the root partition to read and write. In these attacks, basic assumption is that the attacker already has root privilege and the capability to arbitrarily read and write kernel memory. When we remount a root partition, the kernel performs sandbox checks in the function hook mount check remount as we have see in this right figure. And in this hook mount track remount function, the kernel gets the mount flag of the mounted partition and checks whether the flag indicates that this partition is a root partition. If the partition is a root partition, the kernel gets the partition's root vnode and further evaluates sandbox policies. So in order to bypass this sandbox check, we can clear the root partition's flag, especially the root FS and the read-only flags, and then remount perform with the mount system call. After that, we can set the root file system flag again in the mount flag field for this root partition. And this method is said to be proposed by XRAP and has been explained in detail in Jonathan's KitB talk. However, when there is a bypass, we know that there will always be a mitigation. After iOS 11.3, if we use the previous attack method, we will get a kernel panic when we change a file. This indicates a new mitigation in iOS APFS. So what happens here? With root privilege on iOS, let's run the command mount to see how the root partition is mounted. We can see that different from other partitions, there is a strange prefix in the mounted device file path of the root partition. As we can see from what has been shown in the at. So what does prefix mean? Let's do some experiments on macOS. We use an Apple tool called TMUtil, which is short for Time Machine Utilities. In this experiment, we first create a snapshot for the root partition, and then mount the root partition, mount the snapshot onto the temp directory. By running the by running the mount command, we can see that there is also a strange prefix in the in the snapshot mount. So now we can know that the iOS root partition is a snapshot. The prefix represents a snapshot. But what is a snapshot? Apple has explained. Apple explained it as a snapshot is a point in time read-only instance of the file system. The operating system uses snapshots to make backups work more efficiently and offer a way to revert changes to a given point in time. So now we know that on iOS, the root partition is only a point in time read-only instance of the file system. This is the root cause that fails the past attacks and panics the kernel. Even if we modify the mount flag of the root partition to be read and write, the root partition's data structure still represents a read-only snapshot. In this way, we may get a readable but read-only snapshot. That is apparently a conflict. So let's further check what conditions cause the kernel panic. Let's re-examine the panic log. We can find a unique panic string in this panic log. It says, you must have an extend covering allocated sites. By searching this string in APFS binary, we can locate where the panic really happens. The panic happens in this function called alloc space for write with hint. This function is called by APFS handler for file write operation. In this string, we can see a new concept called extend. Actually, extend is a data structure representing a file's location and size. So by reverse engineering, we found that file extents are organized as B trees and stored in the mount data field of the partition's mount structure. And we found that a snapshot mount does not have a valid extend tree in its mount data structure. Even if we can change the mount the snapshot mount flag to be read and write, we cannot find a valid extent in its mount data. So this is the main reason that panics the kernel and causes previous attacks to fail. So what we can do now, as I have said, when there is a mitigation, there will always be a new bypass. So when I discovered about truth, several thoughts for new bypass come into my mind, which has been listed here. I will explain them in detail. The first thought is that maybe we can make another writable mount of the root partition and make changes in the to wanted files in this new mount and then reboot. What we want is that those changes may take effect after reboot, but in fact, this attempt fails because every time after reboot, the root partition will always be reverted to the original snapshot, and all file changes we have made are discarded. Then comes to the second thought. Maybe we can make another writable mount of the root partition and replace the original root v node with the new mounted root. Then the system may look up for files from this new root. But this attempt also fails, since that the system does not traverse from the root v node to look for a v node. So this attempt fails. Then the third thought, as we know, the root cause, as I have explained, is that we don't have a valid extent structure in the mount data field of the root partition's mount. So maybe we can construct a new mount data with a valid extent tree from scratch, representing a writable root partition, and replace the original mount data with this newly constructed one. Also, this attempt fails because that the mount data is too complicated. We cannot create it from scratch. At last, final thought comes into my mind. Instead of creating mount data from scratch, maybe we can ask the system to create a new mount data for us. This mount data is also valid, and replace the original root mount data with the new created one. And here's another question: how to ask the system to create a new valid mount data for us? My solution here is that we can make another writable mount of the root partition and retrieve the mount data from that new mount, and then we can find the valid extents from the mount from this new mount. Here is a figure indicating the procedure of my new bypass. We can see that in the right figure, we mount the root file, the root partition on two directory, and we retrieve the mount data from the new mount, and replace the original mount data with the new mount, and then when the system is able to find valid extents from this new mount data. This is a code for this new bypass. Maybe you can check it later. In this code, there are several details need to be explained. First, the function. There is a function in this code called getVnode@pass. This code is used. This function is used to get the address of a vnode by giving a file path. This function mainly uses the kcall gadget proposed by InBeer to call the kernel function namei. One thing we should note in this function is that after namei is called, we must call vnode put kernel function to adjust the vnode's reference count. This is the implementation of the getVnode@pass. And the second detail in this code is that there are two functions called read kern and write kern. These two functions are used to read and write arbitrary kernel memory. Their implementation can be found in many other open source jailbreaks, for example, as I have listed here. The third detail in this code is that there is a function called mount dev at path as read and write. This function is a wrapper function of the mount system call, but with special mount arguments listed in here later. And these arguments are retrieved by reverse engineering in APFS binary. So now we have writable root partition, right? No, the implementation is not that easy. There are still more checks to bypass. So firstly, iOS does not allow a device to be mounted more than once. My solution to this issue is that we can clear the mounted on flag of the root device vspec flags. Once we clear this flag in this flag, once we clear the mounted on flag in the spec flags, we are able to mount the device for twice or third times or many times. This is the implementation of this bypass. And secondly, there's a pointer in the mount data structure pointing to its belonging mount structure. APFS checks the consistency between the mount structure and the mount data structure. So if we have a mount data structure, but it's the pointer in it does not point to its belonging mount structure, the kernel may panic. So my solution to this issue is that before replacing root mount data, we can set the pointer in this new mount data to the original root mount. Thirdly, what privilege should we use when in the remount procedure? In attacks before iOS 11.3, root privilege is enough. But after 11.3, if we use root privilege, we will get an error like this. This error is caused by a sandbox check. So in order to bypass this sandbox check and solve this problem, I found a detour in the function, in the kernel function, mac mount check mount. In this function, we can use the kernel credential to stop the system from performing further sandbox check. You can see from the code that the kernel checks whether our process has the kernel credential. If we have the kernel credential, it will stop the sandbox check now. So this is the implementation. We can set the pucred pointer in our process to point to the kernel credential. But should we keep using the kernel credential after the mount have finished? If we keep using a kernel credential, the kernel will also panic like this. So why this panic happens? In fact, if an operation target does not belong to the kernel, but current process has the kernel credential, a sandbox will give us a panic. This solution is quite easy. We need to restore the credential of our process to its original after we have called the mount system call. So finally, we can have a successful jailbreak. And in this jailbreak, we can install untrusted apps in applications directory and create files in the root directory. Here is a demo. of our 11.3.1 jailbreak. No, it seems that it's not quite clear. Here, we have installed the terminal and the serial apps in the iOS, and also we are creating a new file in the root partition, in the root directory. We can see that we have successfully created that file. So let's go on. There are two things that we need to especially note in this slide. That the first one is that our solution is only a temporary mount. That means our method only modifies structures in kernel memory and does not modify any configuration files. So after reboot, the root partition will still be reverted to the original snapshot, and all change to files and directories are discarded. The second thing we should know that is that this method was proposed at the time of iOS 11.3. It may not work on iOS 12. Following our method, some others have proposed other kinds of bypass method. All these methods are very brilliant. And Umang has proposed a persistent remounting solution, which is built on a temporary remounting solution, like our method. His method makes changes to wanted files and directories after a temporary remount, as what we have done. And then it renames the root partition snapshot with a dummy name, and creates a new snapshot for the root partition. Then it renames the new snapshot with the original snapshot name. Finally, all files and directory changes will be persistent after reboot. Kustar has also proposed another persistent remounting solution in lecture 11.3.1. His method first makes another writable mount of root partition as what we have done here, and then it renames the original snapshot to a dummy name. Then reboots. The system now cannot find the original snapshot since its name has been changed. Then it will mount the root partition in the old way, in a regular way. So after that, Kustar and the lecturer can use the method in before 11.3 to remount the root partition. So these methods are very brilliant and very powerful. In conclusion, in this talk, I have introduced some basics about Apple file system and explained past attacks on remounting root file system. And I have also shown that how Apple file system has defended against previous attacks, and I also proposed a new bypass method and explained some other bypass methods. That's all for my talk. Thank you. You can follow me on Twitter. And is there any question?
I take it this presumes that you are already root to do these things.
Yeah, as I have said, the assumption is that we already have root privilege and the ability to arbitrarily write and read kernel memory. Yeah. Okay, thank you all guys.